Hi everybody. In this video, I will try to show you how to draw curve graphs by using the derivatives and asymptotes. Here are the examples that we are going to draw graphs of them in this video. So then here we have some more examples from previous times. So these are some kind of graphs that we did draw before. This one is a linear function, so graph of it is a line. So you find 2 points and draw the graph. This one is a quadratic function, so it will be a parabola. You find x-intercepts, vertex, y-intercept, so draw the graph. So then square root of x, exponential function, logarithmic functions. So these are kind of like they have their own paths. We find a few values about them, then draw the graphs. But these are so changeable in too many different ways. So now I will try to show you how to draw such that graphs by using the derivatives and asymptotes. So these first two, they won't have derivatives since they are not defined rationally. And then the C, D in E, they will have some kind of asymptotes. I will also show you how to find those asymptotes over there with these examples. So now let's continue with the first example. We check all of these steps, then draw the graph. The first step, domain. Instead of x, can we use all real numbers from minus infinity to the plus infinity? Is there any number which we can't find a solution for it, which makes it undefined? Since this is a polynomial function, for every real number we will have results, so we can write that x element of real numbers will be the domain. It will be defined everywhere. So then the second step, find the intercepts, which is when x is equal to 0, what is the y value? Simply replace the 0 in the function. 0 cube minus 3 times 0 and minus 2 is equal to minus 2. So when x is equal to 0, the result is minus 2. Then the next thing, what about when y is equal to 0, the x numbers or x number? So now we should equalize this rule x cubed minus 3x and minus 2 to 0 and look for which x numbers can we get the result 0. So right now we should factorize this expression. Since I didn't give you a method to factorize this expression, there is x cubed. If there were x squared, we could try something in here. So I didn't teach you such that method to factorize this one. Actually, there is a path to factorize this, but it takes time, kind of guessing. So if you don't know a clear method, a method to factorize it, you may leave it like that. What I expect from you in exams and quizzes, try everything that you can. For example, in the next question, there is something that we will be able to factorize it by using an idea, which I did teach you in 10th grade. I will expect you to remember that. So now the third step is first derivative. Find first derivative of this function and then increasing, decreasing. X cubed will become 3x squared. Then minus 3x will become minus 3 and minus 2 makes 0 when you take derivative of it. So then we can factorize this expression by moving 2 out, x squared and minus 1. That means we can also factorize one more step, x squared minus 1, kind of x squared minus 1 squared. So it's going to be x minus 1 3 times x minus 1 times x plus 1. So here we have two critical points, which makes it equal to 0. The first critical point is positive 1 from here. 1 minus 1 makes 0. And the second critical point, negative 1 from here. Minus 1 plus 1 makes 0. So then let's do a sign chart for the first derivative. We will be checking for all x numbers which can be used from minus infinite to the plus infinite. So we have two critical numbers, minus 1 and positive 1. In the first row, I will be checking for the derivative. In the second row, I will be checking for the real function. So in the first derivative, minus 1 and plus 1, these are the roots of first derivative. So then I should decide what kind of signs will it have in these intervals. So the way that I decided, I look for the biggest power, which is x squared in here. So it's kind of plus 3 times x squared, kind of positive number. So by looking that from rightest side, we start with plus. Then after each root, we change the sign. So in the other videos that I watched, they are choosing a value bigger than 1, like 2, and checking the result. Will it be positive or negative? Or they are choosing a value between minus 1 and plus 1, like 0, smaller than minus 1, like minus 2. Choose some numbers. If you are not sure about this kind of method, you can find the signs in that way also. So now when you check for the real function, it will be, because of the first derivative, when it's plus, it will be increasing in this interval. Then when it's minus, the first derivative is decreasing in this interval, then increasing again in this interval. So that there is a changing from increasing to decreasing. So there is a maximum point in here. There is a changing from decreasing to increasing. That means there is a minimum point over there in this interval. So let's find those two maximum minimum points, which is f of minus 1 will be the maximum point. So we will replace this minus 1 in real function, in the function which is given in example. So x cube, which is minus 1 cube, then minus 3 times x is going to be minus 1, then minus 2. So the result from this calculation is going to be minus 1 cube is minus 1, minus 3 times minus 1 is plus 3, and minus 2 in here. Minus 1 and minus 2 makes minus 3, plus 3 is equal to 0. This is a maximum value, which we call like local maximum or relative maximum. So then f of 1 is going to be minimum value, which is x cubed minus 3 times x, and minus 2 is the real function. So minus 3 and minus 2 makes minus 5, plus 1 makes minus 4, which is a local minimum value over there. So the third step, checking, we found maximum minimums, we found intervals, increasing, decreasing. So we can move on to the fourth step. Find the second derivative. The result of first derivative over there in here, power 2 will come here, and 3 times 2 is going to be 6 times. It was x squared, so it's going to be x power 1, and minus 3 makes 0 when you take derivative of it. So then second derivative is equal to 0 for which number, which is when x is equal to 0. Let's do the sign chart for the second derivative also. We check for all possible x numbers from minus infinite to the plus infinite. So 0 is the point that may change the thing's signs. So now this row for the second derivative, the next row for the real function. So that when you put numbers bigger than 0, the second derivative will have positive results. It is so visible, and 0 is the root of second derivative. And when you put negative numbers, the result will be negative. With the second derivative, we check the concavity. So then in each interval, it will be concave up or down. When the second derivative is negative, it will be concave down in this interval. Then when the second derivative is positive, it will be concave up in this interval. Also, since there is the changing from down to up, x is equal to 0 is an inflection point. Inflection point. Checking with the second derivative. Now we are done with that. Let's continue with the next step, which is the graph at infinities. Limit when x goes to plus infinite f of x. Then limit when x goes to minus infinite f of x. So if you have a polynomial function like in a row, no rational expressions, you look for the biggest power of x, which is x cubed. Instead of that, when you replace infinite, plus infinite, what about plus infinite to the power of 3? It's going to be a positive infinite. Or let's make the process in here. What about plus infinite power 3 is plus infinite. So then if you replace minus infinite for the biggest power, so minus infinite power 3 is going to be minus infinite. So we look for the biggest power of x, because when you go to the infinite, when you move to the infinite part, so the x squared will not matter anymore. So it will all act by looking the biggest power. So then the sixth step, finding asymptotes. In this one, it is the easiest thing to do, which is this is not rational defined function. In the function part, we don't have any rational expression. We don't have any x values in denominator parts. We don't even have a denominator part in here. So that's why if it is not rational defined function, that means there is no asymptote. So now the seventh step, draw the graph to the plane. Firstly, we put the clear points, we plot the clear points that we found. When x is equal to 0, y is equal to minus 2. Let's put it over there. So then, when y is equal to 0, we have checked for this, but didn't continue in here, so we don't have clear results for this place. So move on, let's move on to the next step. In the third step, we found maximum and minimum point. X is minus 1, result is 0, it's a maximum point over there. The maximum point means that when you draw the graph, it will act like increasing then decreasing. So let's write over there maximum. So then when x is equal to 1, result minus 4, minimum point. Here we have 1 and minus 4. That means the graph will act like decreasing in here, then increasing. Minimum point. I think we didn't find any other clear points. So now by looking concave up, concave down, and increasing, decreasing ideas, we will draw this graph. Also, maximum, minimum points will help us a lot. So there is a maximum point in here. After this maximum point, we will connect those 2 points with curves. So for example, in here, I can connect this maximum point and 2 in this way or in this way. What kind of curve should I use? In this interval, in the place from minus 1 to the 0, what kind of graph should I have? Should it be concave up or concave down? From minus infinity till 0, also this interval means the graph should be concave down. So if you draw this one over there, the graph will be concave up, looking up. So we should draw the first type of line to connect those two. We should draw it in this way. That also, you can also find this from the maximum area. Since it's the maximum point, it should be like a curve in here, a circular curve in here, kind of circle. So That's why it should come from up to down. So how should we continue after 2? Should we continue again in this way, or since the graph should be similar, it seems like also like this. And also there's another way that since this is a minimum point, there should be something like that over there. That's why it cannot come in this way. Also, there is the third thing that you can check it. The graph should be concave up. So you should draw it like as it looks to the upper side. If you draw it in this way, it will be concave down. So now, what about the previous part and after 1, following part? To draw these parts, we will look for infinities. When x numbers goes to plus infinite after 1, the result should increase to the plus infinite also. So we should draw it going up. So when you move up, you should curve it inside. You should curve it inside. You mustn't do such that graph. Some students are making like, they don't care a lot, so they like to finish it very quickly and they draw something like this. If you realize that when you move the arm in the future time, it looks like it's going to be in this way, which means like it's going to change. But the thing that we found in here from 0 to plus infinite, it should always be concave up. So we shouldn't curve. We shouldn't make a curve in the right side. We should continue to make the curve a bit straightly, vertically to up. So let's make it better again. Vertically increasing so slowly, or expanding so slowly. Also, for the previous part, when x numbers goes to minus infinite, the result should decrease to minus infinite. That means you mustn't draw a graph like without caring like this. That also includes the concave down idea. Right now, it looks like it's going to be concave up somewhere here. That means, but actually it should be concave down for all the values from minus infinite to the 0. Similar case like the other side. So we should continue slowly increasing. So now let's move on to the next example. We will try to find the same steps. We'll do the same steps once again for this example. The first step, domain. Since it is polynomial defined, we can use all real numbers. So then after it, intercepts, the second part. When x is equal to 0, what about y number? So in the function, you replace 0. Actually, it is directly the constant number, but let's show that one. Minus 0 to the power of 4 plus 8 times 0 squared and minus 7. If you calculate this one, you will get minus 7. So then the next thing that we should check for the intercepts, what about when y is equal to 0, the x numbers? So here we have the case that I expect you to remember, which is this rule should be equalized to we should equalize this rule to 0. X squared minus 7. We should look for which x numbers we can get the result 0. In the previous function, there was x cubed in here, x to the power of 4 or x to the power of 8 and x squared. If you changing or x squared, we replace another letter like t. I'm going to also move minus out from every term. So it's going to become minus t squared. So when you move, it will be t squared. It's going to be plus 8 times t. So when you move minus 7 plus 8 in here, and you find two numbers which their product is plus 7, their sum is minus 8, which is simply minus 1 times minus 7. Their product is plus 7, their sum is minus 8. So I can factorize this expression as t minus 1 times t minus 7 is equal to 0. So then we can find two results for t, for the new letter that we made. So then we put the x back. We replace t instead of x squared, so that means x squared can be equal to 1 and x squared can be equal to 7. So to get 1 instead of x, we can put two different numbers like minus 1 and plus 1. So these are the critical points. X is equal to minus 1, x is equal to plus 1. So from the 7, we can also find two more results from here. X is equal to minus square root of 7 and positive square root of 7. So now we should do a sign chart for these. Let's do the sign chart in here. Repeat patiently. So I will be checking for all numbers from minus infinite to the plus infinite. Oh, sorry, I shouldn't do the sign chart for this. I will do the sign chart when it's first derivative. I'm very sorry. These were just for the x-intercepts. I'm really extremely sorry. I think they were. So now we should continue with the third step, which is finding the first derivative. Let me start from here. The first derivative of x, power 4 can be moved in here, minus 4 times x to the power of 3, and it was 8x squared. If you move power 2 in here, it's going to be 8 times 2, 16x. So then minus 7 will be 0 when you take derivative of it. So here you can factor out 4x, or let's factor out minus 4x. If you put minus 4x out of parentheses, that will remain inside the parentheses x squared minus 4 times 4. Minus 4 times minus 4 makes plus 16, and we also move the x out. So x squared minus 4 can be factorized one more time, which is x squared minus 2 squared, like x minus 2 and x plus 2. So now from here, we can find three critical points to check. When x is equal to 0, the result is 0. When x is equal to plus 2, and when x is equal to minus 2. So then, since this is the first derivative, we should do the sign chart, which I mistakenly did for the x-intercepts. So how can I separate them? Let's do it with another color. So this is from solution. That's not about the sign chart. So here I should place three numbers, minus 2, 0, and positive 2. So I will be checking for all real numbers from minus infinite to the plus infinite. I'm gonna do two rows in here. The first one for the first derivative, the second one for the real function. So then, since it is in a row, all of these values are making it equal to 0. So they all can be called as roots. So then after the derivative, the largest power is x cubed. Since it is negative, from right side, we start with minus. Then after each root, you change the sign. Plus, then minus, then plus again. Or like the previous one, you may choose some values between those two numbers, like after 2, choose a number like 3, check the result, what kind of result you will have. Between 0 and 2, choose a number like 1. Between 0 and minus 2, choose minus 1. Before minus 2, choose minus 3, minus 4, minus 5, and check the result. It has to be positive. If you want, you may continue to check. So since this is first derivative, these intervals are giving us when does it increase or decrease or increase again or decrease again. So then let's write maximum minimum points from increasing to decreasing. There is a maximum point in here. From decreasing to increasing, there is a minimum point. From increasing to decreasing again, there is another maximum point over there. We should calculate for all these points if they are easy numbers to calculate. If they are not easy, don't force yourself. If they are like kind of like ratio minus 2 over 7 with to the power of 4, don't try so hard. So then let's calculate for this. Minus times minus 2 to the power of 4 plus, but actually as an additional thing, if you are making a university exam, you have to find, even if it is minus 2 over 7, you must find those results. But for my exams, it's not so problem, big deal. Minus 2 squared, 8x squared, and minus 7. Let's calculate this one. So minus 2 to the power of 4 will be plus 16. Minus 2, yes, will be plus 16 times minus, and completely minus 16 we will have in first place. Then in the second place, minus 2 squared will be 4. 4 times 8 will be 32. So 32 minus 16 makes 16. Then minus 7 makes 9, which is the maximum point. So then the minimum point when x is equal to 0, we have minimum point in here. I couldn't write so well, sorry about that. F of 0 is the minimum point. We should calculate for that, which we already have done in the beginning, which is equal to minus 7. It's a minimum point. So then we should calculate for f of 2. And you calculate for f of 2, it's going to be minus x to the power of 4 minus 2 to the power of 4 and plus 8 times 2 squared, x squared, then minus 7. And the result is going to be equal to 2 to the power of 4 is 16. It's going to be minus 16 plus 32, which is plus 16, then minus 7 makes 9, another maximum value, which we call local maximums in here before we complete the graph. So then let's move to the next step. The checking first derivative is finished right now. So now the second derivative, let's check for that. The result of first derivative over there in here. I will take another derivative of this expression, which is power 3 will come here as product. 4 times 3 is going to be minus 12. It was x cubed, so then x squared going to be, and plus 16x will become plus 16. Firstly, we equalize this one to 0. 0 equals minus 12 x squared plus 16. So then normally we try to factorize, but for this case, we may use another method. Move minus 12x squared other side. It's going to be minus 12x squared will be plus 12 times x squared, and 16 will remain inside. It's going to be plus 12, which can come here as over 12. I did 2 steps at once, which also when you simplify by 4, which is 4 over 3. If I do it quickly, x squared is equal to 4 over 3. So for x, we can find two numbers. It can be negative square root of 4 over 3, or it can be positive square root of 4 over 3. So then let's do the sign chart for the second derivative. I think the things in here will disturb that one. Let's delete those. So then I'm checking for all the values from minus infinite to the plus infinite. I have two clear numbers, minus square root of 4 over 3 and plus square root of 4 over 3. These are the roots of the second derivative. I'm checking for the second derivative. Then the next row for the real function. So these are the roots. So x squared is the largest power in second derivative, so it's minus 12 times x squared. From right hand side, you start with minus, then plus, then minus again. So then, since second derivative is about concave, so when it's minus, it's going to be concave down in here, concave up over there, then concave down in this interval from square root of 4 over 3 to plus infinity. It will be concave down. So these are also called inflection points. X is equal to minus square root of 4 over 3 plus square root of 4 over 3. They are also called inflection points. We should find results for them, but since, as I have told, kind of it's going to be take so much time, so no need to find for this kind of results. If it was like just one, we could try. Actually, it is a very close number to the one, like 3 over 3, 4 over 3. It's very close to 1. Anyway, this was the fourth step. So then let's go to the fifth step, the graph at infinities. Limit when x goes to plus infinite for this function. So the largest power over there, minus times in the real function, minus times x power 4. So minus times infinite power 4 is going to be minus infinite. So then if you do the checking for negative infinite, also limit x approaches to negative infinite f of x. So we should replace this negative infinite in the largest power, which is negative infinite power 4. Negative infinite power 4 will be positive result times minus, it will be negative infinite also. We did the fifth step, then the sixth step. Let's write in black in here, the sixth step. For this function, it is very easy to write, which is find asymptotes. Since this is not rational defined function, there is no asymptote. So now let's draw the graph. Firstly, the clear points that we found. When x is equal to 0, result is minus 7. Over there in here. So then, when y is equal to 0, we have found 4 x numbers, x-intercepts, which is x is equal to minus 1, x is equal to plus 1. Then square root of 7 can be written between 2 and 3, which is square root of 4 and square root of 9. Square root of 7 should be somewhere at this point. Square root of 7. Then minus square root of 7 should be somewhere at this point, minus square root of 7. That means the graph will pass through all of these points. So then any other point that we found from third step, yes, there are maximum and minimum points. When x is equal to minus 2, result 9. When x is equal to minus 2, the result 9 is a maximum point like we talked before. It's going to be a curve in here in this way. Then when x is equal to 2, another maximum point, which is when x is equal to 2, result is positive 9. Sorry about that. So another maximum point. So when x is equal to 0, minus 7 is a minimum point. We already have showed that one. So let's write that this is going to be a minimum point. Let's draw the graph. Firstly, let's connect the clear points. I will not be talking about concave up, concave down, and increasing, decreasing, which is we will connect these points with curves by using maximum and minimum points. So increasing, decreasing ideas and concave up and concave down, they satisfy our solutions, our drawing. For example, let me connect those as much as better that I can do. It's very hard to draw it in here, but it's going to be curved. There is maximum, then it will be going down, 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 going through from this point. Then I should continue with this similarly. Then from decreasing to increasing, it will change its path. Then it will go through 1. Then there is maximum point. We should go up to the maximum point. Then decreasing, going through 7. So from minus infinite to the minus 4, minus square root of 4 over 3, till that point, somewhere here, somewhere like minus 1 over there. So in this interval from minus infinite, actually, so the graph should be concave down, then between those two concave up, the second part concave up, and the third part concave down again. That also means that when I continue, I should continue as concave down. I should continue as concave down. I mustn't move the graph like to the other side. I should continue to keep it concave down. Also, the fifth step helps us, which is when x goes to plus infinite after this square root of 7, the results will be approaching, will be going to the minus infinite to the down. When x numbers goes to minus infinite, the results are going to be minus infinite. So the graph should continue in this way. Now, before we move to the next example, I want to talk about the asymptotes. How do we understand? How do they help us? So when you draw the graph from left to the right, when you reach around the asymptote, vertical asymptote, the graph should turn up or should turn down. It should do one of them. You should go up or go down. That's the idea of vertical asymptotes. If you are drawing this graph from right to left, whenever you get close to the vertical asymptote, you should be moving up or moving down. It will never cut the vertical asymptote. For example, if you found a minimum value in here, let's say you have a minimum value in here and maximum value over there. If this is maximum value and let's say there is no more point, or let's say here you have a maximum point, let's say, and this was maximum, I have minimum. How can we draw such a graph? So since this is maximum, it will be something like this. Since this is minimum, it will be something like this. If you can connect them, imagine that they will be connected like this. So since this is minimum, so it should go up, and this arm should go down. Since it's maximum, there mustn't be any more minimum in here, since we didn't find, or I didn't write it over there. If this is maximum point, we should have something like this. That means this arm will go down, the other arm will go down also. Since there is not another minimum point in here, it will go down also. So how do we understand, how do we use the horizontal asymptotes? The horizontal asymptotes, they are only about the infinities. When x numbers goes to minus infinite, so the graph should approach to the horizontal asymptote from upper side or from lower side. Also for positive infinite, it should approach from upper side or lower side. So the between in here, it's not problem. It is only about the infinities. So let's say for the first idea, I have a maximum point, minimum point in here, and I should draw this graph. So the maximum point will be connected, the minimum point will be connected in this way. So if you do connect them, so after minimum, since the graph should approach to somewhere at infinite, it should approach to horizontal asymptote, you cannot move it up. So you should make it like approaching to the horizontal asymptote. So after the maximum, since it cannot go down to infinite, it should approach to horizontal asymptote. That's why you draw it in this way. Let's say we have another points, some more points. Here we have a minimum point, maximum point, another minimum, and another maximum, let's say. So it will be in this way, in this way, this way, and in this way. So when you connect the maximum, minimum, maximum, then another minimum, then another maximum. So how will it go in the right side and left side? So since we have the maximum in here, it can't go down anymore, so it should approach to horizontal asymptote from up. So then since this is minimum, there cannot be another maximum over there. So it will approach to horizontal asymptote from lower side. So now, what if you have them both in one place? What kind of graphs we can have? So it will come from here, it will come from there. If you have something increasing, you will start from here and increase it to the up. If you have something decreasing, you will start from here, decrease it to down. So then, between part, after the vertical asymptote, you should start from top or down. So you will choose this one. After -2, the graph, is it increasing or decreasing? If you have a decreasing graph, you will start from top and then to continue. If it continues to decrease, you will keep decreasing it to the other vertical. But if you have a minimum point in here, if you have a minimum point, if you found a minimum point, so it will be decreasing after the minimum point, it should change to increasing back. So what about the third case? Third part in here. So after +1, there is +1 in here. You check from first derivative. After +1, the graph, will it be increasing or decreasing? If you have a graph, let's say we have after 1 increasing, so I can't start from top. When I start from top, I have to go down. So I start from down and go up, so the graph will be in increasing way. So now let's move on to the example. Here we have the first example with the asymptotes. First thing, the domain. If you have rational defined function, the denominator can never be 0. 2x plus 4, when it is equal to 0, it will be undefined, which is when x is equal to -2. I think you can find it so easily. That means the domain, all real numbers we can use, but not -2. The first step. So then the second step is about finding the intercepts. When x is equal to 0, find the y result, find the y value. F of 0 is equal to 0 minus 3 over 2 times 0. Let's make it better. 2 times 0 and plus 4. You will find minus 3 over 4 to find number. Now, what about when y is equal to 0, the x number? What should it be? Which is, we will equalize the function, which is x minus 3 over 2x plus 4. We should equalize it to 0. So right now, actually, there are several kind of paths that you can continue, but I will do it quickly at one step, which is you may do like multiply both sides by 2x plus 4. 2x plus 4 times 0 is 0. Then 2x plus 4 times the left side, they will simplify each other. Or write 0 over 1 and do the cross product. So I will do quickest idea, which is to make this rational expression equal to 0, it should be something like 0 over a number. So the numerator part should be equal to 0. If x minus 3 should be equal to 0, so when x is equal to 3, the result will be 0. The second step is done also. Now, let's continue to the third step. Third step, the first derivative. Let's do it up in here. We should find derivative of this function. That is the long part with the rational expressions. So here we have a rational expression. So the idea is we will use the quotient rule. Derivative of numerator part, derivative of x is 1 times the denominator, same again in here, 2x plus 4. Then minus numerator, same again, x minus 3. Then derivative of 2x plus 4 is 2 over the denominator squared, which is 2x plus 4 in denominator. The first derivative of x is equal to, we are sure about that, 2x plus 4 squared will be in denominator. So now let's calculate this one. 1 times 2x is going to be plus 2x. So 2 times x we will have in here. So then minus 2x minus 2x will be 0. Then the number parts, 1 times plus 4 is plus 4. Then minus times minus 3 is plus 3 times 2 is 6. 6 plus 4 makes 10. That will be only 10. So the second derivative can never be equal to 0 since we have number 10 in here. But when x is equal to minus 2, it will be undefined. The denominator will be equal to 0. It will be undefined. So let's make a sign chart for these. All x numbers. Minus 2 is a critical point that may change it, We are checking for first derivative in here. So then, at plus infinite, if I use my idea in here, using the idea that I gave, it can be a bit tricky in this place. When you put plus infinite squared will be positive, so plus 10 is also positive. You will start with plus. There is the problem in here, which is the number that minus 2 that I have found. It is found from this expression 2x plus 4. So there is 2x plus 4 is inside of a parenthesis, and we have all power 2. If you have power 2, we call it as even root. When it's even root, that kind of roots, that kind of critical point doesn't change the sign. It will be plus again in here. But you can find these values by checking some numbers. Check a number bigger than minus 2, like 0. When you put 0, you will have a negative result. Check a number smaller than minus 2, like minus 3. 2 times minus 3 is minus 6. Plus 4 makes minus 2. Minus 2 squared will be positive, so plus and over plus, it will be plus, positive result. So the real function is increasing in this interval, is also increasing in the second interval, which means for all x numbers, the real function will be increasing. So now we can move to the fourth step. F of, let's write number 4 over there. Fourth step, second derivative of x. So there are two kind of ways that you can find this second derivative. I will do the one that I think you can understand easily. So the other method that I am not going to do, we can move this all parentheses up. It's going to be all with parentheses and power minus 2, and we can use general power rule directly, then move it down again. But I will use like rational functions. So when we do it like that, first we write derivative of numerator. Derivative of 10 is 0. Derivative of constant number. Then denominator same again. 2x plus 4, all in parentheses and power 2. So then minus. Numerator same again, which is 10, times derivative of denominator, all inside the parentheses and power 2. We use the general power rule. Firstly, we move power 2 before the parentheses, and then to the power of 1, we write over there. The part inside the parentheses, which is 2x plus 4, we keep it same. Then, if you use the general power rule, that means there is another function inside the parentheses. We should multiply this by derivative of inside part, which is 2x plus 4. Derivative of it is 2. So then the denominator power 2. It was already all in parentheses and squared. If you take another square in here, it's going to be 2x plus 4 to the power of squared will be power 4. So now I have second derivative of x equals, this part is going to be 0. The other side, 2 times 10, 20, times 2, 40. It's going to be minus 40 times 2x plus 4. And the denominator, 2x plus 4 to the power of 4. If you simplify these two, since they are exactly the same inside the parentheses, you will have minus 40 over 2x plus 4 to the power of 3. So now we can find the critical value to make the sign chart, which is this second derivative is equal to 0 or undefined for which number of x. It can never be 0. But when you put minus 2 instead of x, similarly in here, it's going to be undefined. Let's also remove these two from there. So we can have a place to be able to write. So from here, we can say that when x is equal to minus 2, it is undefined. So we can do a sign chart for these by using minus 2. I will be checking for all x numbers from minus infinity to the plus infinity. So I am checking for the second derivative. In the next part, that will be the things about the real function. So now we are checking the signs with my idea, which is if I put plus infinity here, plus infinity cube will be a positive number, minus over positive number will be a negative result. So after minus 2, should it change the sign or not? So I look for that. I got the result minus 2 from all in parentheses and power 3. Since it is an odd power, the sign should change to the plus in here, from minus to plus. So the other idea, if you try a number bigger than minus 2, like 0, it will be 4 cube positive, minus 40 negative. So minus over plus is minus. If you try a number smaller than minus 2, you will get negative result in here, power 3 negative, minus over minus will be plus. So then with the second derivative, we check the concavity, which is when it's plus, the real graph should be concave up, when it's minus, the graph should be concave down. So checking the fourth step is finished. It is time to fifth step. Yes, I did use this color. Now let's go with black. In fifth step, we should check the infinities. Limit when x goes to plus infinite. Limit when x goes to minus infinite. So the real function, f of x. So this is something about limits, but it's very easy thing. So I want to show this thing. I want to show you there are 3 cases for rational expression. I want to show you all of them at once. So let's go back and see all the examples in one page. So here we have 3 different cases. The degree of numerator, which is the highest power, x to the power of 1. The degree of denominator, the highest power, x to the power of 1. If they are exactly the same, we take ratio of coefficients. In this example, right now we are solving, it's going to be 1 over 2. But if you have a case like this, next example, highest power 1, highest power 2. If denominator's degree is bigger, so it will be approaching to 0. If you have the next case, numerator's degree is bigger than denominator's degree, that means it will be approaching either plus 1 or plus infinite or minus infinite. So we should check, will it be plus infinite or minus infinite for each cases. Now let's go back to the example that we are solving right now. So it's exactly that I have told. Since they have same power, we take ratio of their coefficients. It's going to be 1 over 2 in both cases. This also gives us, if you find a number result like 1 over 2, like 0, like 3 over 4, when you check for the infinities, that means it is the horizontal asymptote. Let's make a very nice one in here. Drawing I have. It is horizontal asymptote. Which is we show as y equals 1 over 2. This was the fifth step. So now Final, the sixth step, find asymptotes. So now we already have found one asymptote, which is the horizontal one from the fifth step. So if we have a horizontal asymptote, we won't have oblique asymptote. I didn't talk about that in the previous page. So after this example, I will talk about that also. So then the other asymptote that we should check is the vertical asymptote. Vertical. The vertical asymptotes when the denominator 2x plus 4 equals 0, which is x is equal to minus 2 is the vertical asymptote. So we found and done. Now the final thing, draw the graph. Let's check that. Did we find any clear point? When x is equal to 0, the result is minus 3 over 4, like minus 0.75 minus 3 over 4, somewhere in here. Did we find another result? When x is equal to 3, y 0. Another point in here. Did I find maximum minimum points from first derivative? No, not inflection point. So why not minus 2 is inflection point? Let's go back to that topic. Because when you replace minus 2 in real function, you can't find the result. It is undefined. There is no result. There is no point on the graph like that. It can't be inflection point. So then let's move on. After putting the clear points, if there are asymptotes, we should draw their lines on the graph. The first asymptote, the horizontal one, y is equal to 1 over 2. 1 over 2 half in here. It will be 1 over 2 everywhere. 1 over 2, 1 over 2, 1 over 2, 1 over 2, 1 over 2. For all x numbers, we will have 1 over 2, which we call as horizontal asymptote. So then vertical asymptote, which is when x is equal to minus 2. It is time to draw the graph. So let's start from left side. Since this is horizontal asymptote, at infinities the graph should approach it from upper side or from lower side. Let's check that. If I start from upper side to draw, that means I'm going to increase it to up, since there is also a vertical asymptote over there in here. So in this interval, also if I start from lower side, that means when I move forward, I will go down, since also there's a vertical asymptote. That means the real graph will be decreasing or increasing. Let's check it from first derivative. Should it be increasing or decreasing? The first derivative says that it should be increasing. That's why I start from upper side. Then when I get closer to the vertical asymptote, so I move it up, which is an increasing part. From minus infinity till minus 2, it's increasing. Let's confirm this one from the concave idea. From minus infinity to the minus 2, the graph should be concave up. Concave up. If I would draw the other one, the graph would be concave down, so it can't. So now after minus 2, I should start from top side or lower side, bottom side of the vertical asymptote. So now also you can see that since we have two clear points in here, I should start from here. And there is another idea. Check it from the first derivative. The graph should be increasing. If I start from top, that means I should continue to down. The graph will be decreasing, so it can't be. That's why I start from lower side and the graph increasing, passing through these 2 points. So after 3, guess what should it be? Since there is a horizontal asymptote, it should get closer to the horizontal asymptote. As you see, the graph is increasing in this interval also. And then let's check the concavity. It should be concave down from minus 2 to the plus infinite. So this question is done. Before I move to the next question, there was something that I forgot about the asymptotes, which is oblique asymptotes. If there is given a function like rational function, if numerators degree, let's say 3 in here, 3x in here, if it is just 1 bigger than denominators, that means there will be oblique asymptote. But if it is like 2 bigger or 3 bigger, it's not happening. Only one case. If it is just 1 bigger, like x squared, x cubed, or if you have x power 5 in here, x power 5, there should be x to power 4 in here to have an oblique asymptote. Oblique asymptote means that it will be a line kind of like this. We will call it as oblique asymptote. So when you draw the graph, if you start from top side, you will have somewhere here a minimum point. You won't be passing this line, you will be approaching that line in infinite. And probably the other side will be in this case. Or you may have them in this case. If you start from down, the graph will be approaching to oblique asymptote at infinity. It will be similarly in the other side, probably. So now we will check that on an example. In the last example. So now, example B. We should again do the steps. The first step, domain. Since we have rational defined function, the denominator cannot be 0 at any time, which we can factorize as like 2 squared x minus 2 x plus 2 is equal to 0. So then there are the two roots, x positive 2, x negative 2. That means the domain, all real numbers can be used, but not minus 2 and positive 2 cannot be used in this function. The second step, intercepts. So when x is equal to 0, check y. What about y? So f of 0 is equal to 0 over 0 squared minus 4. So 0 over a number will be 0. If I look for the next one, when y is equal to 0, what about x? Actually, right now, I am looking for exactly the same thing that I have found in here. When x is equal to 0, the result should be 0. That means if you check it when y is equal, what should be x? So x should be 0. Actually, we are checking the same thing once again. So no need to calculate. Now the third step, first derivative. F derivative of x is equal to rational quotient rule, derivative of numerator 1 times x squared minus 4, the minus between them, the numerator same, x times derivative of denominator, x squared, derivative of it is 2x, and minus 4 will be 0, derivative of minus 4. So then in denominator we will have x squared minus 4, all in parentheses, and power 2. First derivative of x is equal to 1 times x squared is x squared minus x times 2x will be 2x squared. So that means there will be minus x squared. So the number part 1 times minus 4 is minus 4. Over x squared minus 4 squared. So check that in numerator they are both minus. So if I put the minus out, it will be positive x squared inside the parentheses and positive 4 inside the parentheses. So I did another step in here directly. Later we check that for which numbers will this be equal to 0 or undefined. So the numerator part can never be equal to 0 since x squared positive, then plus 4, never 0. But the denominator, when it takes values minus 2 and plus 2, minus 2 and plus 2, like we have done in here, So it will be undefined. When x takes values -2 or +2, it will be undefined. Let's do a sign chart for this. Let's check increasing, decreasing idea. So all numbers from -infinite to the +infinite, -2 and +2, and in this row I will be checking for signs of first derivative. Now -2 and +2, they are not rules, they are making undefined. Let's check the signs. So when we put +infinite in this one, +infinite squared, and squared will be a positive number. There is positive number times minus will be minus, but it's going to be negative in here. Later I checked that. I found -2 and +2 by using the inside part of this parentheses. Since we have all in parentheses and power 2, they will be odd root. They will be even roots. That's why the sign will not change for any one of them. It will be always minus. So if you want to check it with different method, like with numbers, you can put number 3 and find the result. It will be negative result. You can try 0, it will be negative result as well. And then you can try -3, it will be negative result as well. If you can't get my idea, no problem with that. It just takes time. So now the real graph, decreasing, decreasing, and decreasing, since all of them are minus. But there is no maximum minimum points to calculate. The third step is also done. So now let's continue to the fourth step, the second derivative. We will need a place for that. Let's try doing it in here. Let's try. I hope that I can fit it in here. The second derivative. 1, 2 equals. We have a rational expression in here. We should do like that. It will take so much place. But I hope that I can do it clearly. First thing, derivative of numerator. Derivative of x squared is 2x times minus 2x times denominator same again, x squared minus 4 power 2 same again, minus between them, the numerator same again, which is minus times, let's keep it like this, minus times x squared plus 4. This is the numerator. We write it same again in here. Then times derivative of denominator is all in parentheses and power 2, general power rule. Power 2 comes here. We keep the parentheses same, times derivative of inside parts, which is x squared. Derivative of x squared is 2x. So what was there inside parentheses? X squared and minus 4. So then all of them over x squared and minus 4. So in the beginning, after first derivative, we have power 2 order in here. If you take another power 2, square of square, so going to be power 4. So then in here, look at that. This minus separates like the first part, the second part. In the first part, we have the 2x factor. In the second part, we have the 2x factor that we can put it out. Here we have the factor x squared minus 4 power 1. Here we have x squared minus 4 power 2. So we can move one of them out. X squared minus 4 out. So then times inside the parentheses. So from first place, I will be moving 2x out. Minus remains in there. Then there is power 2. I will move one of them out. The other will be in there. So when you multiply the other by minus times x squared, minus times minus 4 will be plus 4. Let's check about the second part. 2x will be moved out, x squared minus 4 will be moved out. So here we have left with minus times minus plus times 2. So 2 times x squared plus 2x squared 2 times plus 4 is 8. Let's close the parentheses. Or brackets, I think we call that one. Like in the previous example, if you see that, here we have same thing inside the parentheses. When you simplify them, there will be over cube in here. It's going to be x squared minus 4 to the power of 3, and 2x remains up there. What about inside the brackets? 2x squared minus x squared is 1x squared. So then 4 plus 8 makes 12. So this is the second derivative of x, f of x. Now, the numbers that I should check in here. When 2x is equal to 0, which is x is equal to 0, this makes the whole expression 0. And then the inside part, when x squared minus 4 is equal to 0, which is x is equal to minus 2 and plus 2, it makes it undefined. So when I check, I will be checking for, let's close all of those parts, they were useless then. So should I try to fit it in here? Let's try to fit it in here. So I'm gonna do a sign chart for the second derivative. There will be 3 numbers to check. I can't draw it so straightly, it's so bad. So then minus 2, 0, positive 2, and positive infinite in here. Second derivative. Let's go with my idea. If I put plus infinite, it is always positive in here. It will be positive 2 times plus infinite. What about the denominator? Plus infinite squared, positive, cube, positive. So plus over plus is going to be plus. So then, after 2, should I change the sign? Since I found the 2 from cube, it is an odd power. That's why I should change the sign. What about 0? It is also x power 1. So change the sign again. This also can be called as root. So then what about minus 2? I found it from cube, so we should change the sign. As I have taught, you may try some numbers between those or up to like 3. You will find exactly these signs. I hope that I don't have mistake at that. Probably I don't have. I trust in myself. So now, with the second derivative, we check concave up and concave down. When it's minus, it's going to be concave down. When it's plus, it's going to be concave up, concave down, and up again. So these are all about concave. So which one of those points can be called as inflection point? When you put minus 2 in the real function, you can't get the result. So there is no such that point on the graph. That's why it can't be an inflection point. But it seems like from down to up changing, it should be inflection. So what about 0? Yes, we can use 0 in the real function. So 0 is inflection point. Inflection point. What about number 2? It cannot be used in real function. There is no point in real function, so it can't be inflection point on the real graph. This is the fourth step. This was the fourth step. So now the fifth step. Infinities. Limit when x goes to plus infinite. Limit when x goes to minus infinite. F of x. This is the second case that I was talking about. I did talk about if the denominator's degree is bigger than numerators, so it will be approaching to 0. If you find a number from checking infinities, that means it is the horizontal asymptote. Horizontal asymptote, which is y is equal to 0. Checking infinities finished. So now it is time to check for the asymptotes. We already have found one, so we should check for vertical The vertical asymptote says that the denominator x squared minus 4 cannot be equal to 0. So x is equal to minus 2 and x is equal to positive 2 are the vertical asymptotes. Let's draw them. So in here, let's start with drawing asymptotes. The horizontal one, y is equal to 0. That means everywhere the y number should be equal to 0. That line is the horizontal asymptote, which is the x-axis itself. I couldn't do it well, but anyway. So then x is equal to minus 2 and plus 2 are the vertical asymptotes. Let's increase the size of the points, then it can be quick to me. I can do it quickly. So then x is equal to 2 is another vertical asymptote. It is time to draw the graph. So I think there was a clear point in here when x is equal to 0, y is equal to 0. I don't remember finding another clear point. There is no maximum minimum. There is no any other intercept in here. So now let's start from minus infinite. We should start from upper side or lower side. So how do we decide that? By looking increasing, decreasing. Let's go there. When you start from minus infinite till minus 2, it should be decreasing. Actually, it is decreasing at every point. So if I start from upper side, I must make it increasing. So I can't make it increasing. That's why I should start from lower side and decrease. Since this is also vertical asymptote, it should go to minus infinite over there. Let's check this one from concavity, which is from minus infinite till minus 2, it is concave down, looking down. Yes, it's good. That the thing we did draw. So then after this one, after minus 2, since I have a vertical asymptote, I should start from top side or bottom side. So if I start from bottom side, the graph will be increasing, but the first derivative says that it should be decreasing again. So how should I decrease that? Actually, since this is vertical asymptote, we must do it in this way. So it should be like a bit closer. So it should approach to x at infinity and later going to this point. But there are some people might think that what if it is in this way? So we check that from the concave idea. From minus 2 to the 0, the graph should be concave up. If you draw this second one, it is concave down, so we can't draw it. The first one that we did draw, it's concave up, so true. So then after 0, the graph should be concave down. That means I should continue to the graph as the concave down. I shouldn't continue like concave up again. So then the next curve, where should we start? Since we have another vertical, after vertical, we should start from top or bottom. Since it should decrease after 2, it should decrease again. So we should start from top part and decrease, 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 decrease. Since we don't have any minimum points in here, it won't cut this line. That's why it will be approaching to the horizontal asymptote at plus infinity. So now the last question for this video with oblique asymptote will be the firstly the intercept, the domain. The x can't be 0. We can use all real numbers, but not 0. Sorry about my handwriting, there is 0 in here. So then the second step, intercepts. When x is equal to 0, there is no y number since we can put it over there. What about when y is equal to 0? Can we find the next number? Check that. So x squared plus 1 over x is equal to 0. Let's use the normal steps in here. Let's write 0 over 1 and to the cross product. This part times 1 is x squared plus 1. And x times 0 is 0. X squared can never be equal to minus 1 in real numbers set. So there is no intercept. Then the third step, first derivative. Let's find the first derivative. Where? Let's find it over there in here. I hope that it's short. So derivative of numerator part, quotient rule, 2x times denominator, same again, x. Then minus numerator, same again, x squared plus 1. Since it is plural, we should keep it with parentheses. Then times derivative of denominator, derivative of x is 1 over denominator power 2. So then 2x times x will be 2x squared, and minus x squared will come from there, so it's going to be x squared. Minus times plus 1 will be minus 1, and x squared minus 1 from there over x squared. So then we should find the values making the first derivative equal to 0 or undefined. That's why let's factorize this expression. X squared minus 1 can be factorized as x minus 1 and x plus 1. X minus 1, x plus 1. Let's save some place. Let's delete all of these things from the house. Over all x squared. So from here we can find 3 critical points. The first, when x minus 1 is equal to 0, x is equal to 1. When x plus 1 is equal to 0, x is equal to minus 1. When x squared is equal to 0, x is equal to 0. Okay, that I found this from x squared, so this is like double. So it won't change the sign when I do the sign chart. Let's do the sign chart for the first derivative. We will check all real numbers from minus infinite to the plus infinite. So the numbers that critical ones, minus 1, 0, and plus 1. So let's make them a bit longer. Here I will be checking for first derivative in this row. The signs of it, so minus 1 and plus 1 can be called as roots, but the other one, that's the critical point, makes it undefined. So now let's start from plus infinite part. After the derivative, this is something that I can work with. If I replace plus infinite in this equation, in this function, plus infinite squared is a positive, plus infinite squared is a positive number. So I will start with plus. After this one, after 1, I will change the sign, but after 0, I will not change the sign. So then after minus 1, I will change the sign again. So only with 0, I didn't change the sign. So let's check my thinking. Is it true or not? What if you replace like plus 1 over 2? 1 over 2 squared is 1 over 4 times minus 1 will be negative number. Negative over it will be positive, so negative. What if you replace minus 1 over 2? Minus 1 over 2 squared will be plus 1 over 4. Plus 1 over 4 minus 1 will be a negative number. Minus 3 over 4 over positive will be negative, as you see over there. You may also check like a number bigger than 1, 2, a number smaller than minus 1, minus 2. So now the real function in here, it will be increasing, then decreasing, then decreasing again, then increasing again. Do we have any maximum minimum? From increasing to decreasing, here we have a maximum value. From decreasing to increasing, here we have a minimum value. Let's calculate those two, which is f of minus 1. Let's be fast. What if we calculate minus 1 squared will be plus 1, plus 1 plus 1 makes 2. 2 over minus 1 is going to be minus 2. What about f of 2? What kind of value was this? Minus 2 is maximum. What about f of 1? What about this? So 1 squared is 1, 1 plus 1 is 2, 2 over 1 is 2. It's a minimum point. So this was the third step. So now the fourth step. Another derivative of this function. Second derivative equals. So quotient rule. From here, I will take the derivative, not from the other ones. So these are all equal to each other for the first derivative. So derivative of numerator part x squared is 2x. Actually, guys, this now is enough for us right now. We could continue with the asymptotes, but let's complete all the steps. So then the denominator same again, x squared. The minus, you keep the numerator same, x squared minus 1 same. And then times derivative of denominator, which is 2x. Then denominator, there was x squared. When you take another square of this, it will be x to the power of 4. Let's make it clear. So it is 2x. We have 2x in both places. So we can take 2x parentheses. If you take 2x parentheses, what will it be over there? X squared from first. From second, minus times x squared minus x squared. And minus times minus 1 plus 1. And let's close it. X to the power of 4. So now if we write the final x and x power 4 will simplify each other. And like the previous ones, for the second derivative, it will be cube in here. So then number 2 remains in here times 0 plus 1 times 1. The second derivative. Luckily, there is only one value to check, which makes it undefined when x is equal to 0. Let's do the sign chart. When x is equal to 0, the second derivative, all x numbers from minus infinity to plus infinity. Let's start with plus infinity. If you put plus infinity in here, plus over plus is going to be positive plus. So then let's close this one. Since the 0 comes from cube, it's an odd power. That's why the sign will change. The real function will be concave down in this interval and concave up in that interval. And 0 can be replaced 0 in the real function. Can we get a result for that? So over 0 we can't write, so 0 cannot be an inflection point. The next step, checking the infinities. This was 4 and 5th. Limit when x goes to plus infinite. So right now, f of x, we should compare the highest powers from both. Infinite squared is the highest power over infinite. So if the numerator's degree of numerator is bigger than denominator, we know that the final result will be infinite for the limit. Right now, I am only checking for, will it be plus infinite or negative infinite? So positive over positive, when x numbers goes to plus infinite, the results will be plus infinite. And the limit when x goes to minus infinite, let's put minus over there, f of x. So we only compare for the highest powers, which is minus infinite squared over minus infinite. So I'm sure about that it is going to be infinite. I'm only looking for, will it be plus or minus? Minus infinite squared will be positive, so plus over minus will be minus infinite. Right now, from checking limits, we didn't find any number. That means there is no horizontal asymptote in here. Let's close this one. So now the final case, the sixth one, asymptotes. So firstly, the vertical asymptote. When the denominator is equal to 0, x is equal to 0, we directly found it. Right now here we have the case. The degree in numerator is only 1 bigger than the denominator's degree. That's why we will have an oblique asymptote. So to be able to find oblique asymptote, we simply divide these two polynomials, x squared plus 1. That is something that we did when we were in 10th grade, guys. Divided by x. We have made a lot of further examples. Let's try doing this one. So from x, to get x squared, I should multiply it by itself. X times x will be x squared. So when you subtract them, it's going to be 0 and plus 1. Here in the remainder part, if I would still have x, something like 2x in here, I would continue by multiplying 2. But right now there is no more x in here. That means the division is finished. The result of this division, the quotient, is the oblique asymptote, which can be written as y is equal to x. So now let's finish this video by drawing this graph. First, vertical asymptote, the y-axis itself. Let's make the point one bigger. X always 0, x 0, x 0, x 2, x 2, everywhere x 0. The y-axis itself is the vertical asymptote. So that oblique asymptote y is equal to x. It's another line, y is equal to x at every point. I don't see it so clearly. So now, did we find any clear point about this graph? Let's check that. From here, no. Yes, we found maximums and minimums when x is equal to -1, result -2. It is a maximum point. This is a maximum point. So then when x is equal to 1, result is 2. The result is 2. This is a minimum point. Did I find any other clear points? No. So now it is time to start to draw the graph. So right now I will not start from infinities. I will start from around the vertical one, because since it is not horizontal asymptote, it may be a bit hard. So let's do only the let's start with the positive part. So after the vertical, should I start from top and bottom? There are two things to decide. Since we have a clear point in here, that means I should start from top. The other thing over there, that means in this interval, after 0, it will be decreasing till 1. Until we get 1, it will be decreasing. So you start from top part, it will be decreasing. After, when x is equal to 1, after that, after 1, it will continue as increasing. So the idea of oblique asymptotes, normally we could draw that increasing up like that. So we don't draw it in this way. So we draw it, it will be increasing, and while it increases, it will be approaching to this line. It never cuts the line. Make it a bit better shape. So then it will also be concave up in this interval, concave up. So if you turn it down, then it's false. So then the other side, if I start from like 0 to the left side, from 0 to the -1, the graph should be decreasing. That means I should start from here and go back there. Check that if I do it in this way. So to check that from -1 to the 0, the graph is decreasing to the minus infinity. So I did it in this case. So before this, it should be increasing. It should be approaching to this asymptote. So then let's check that. From left side, the graph starts like increasing, then decreasing. After the vertical asymptote, it jumps up. So then decreasing, still decreasing till 1. After 1, continues to increase. So then concave up and down. from minus infinite to 0, it is concave down, and from 0 to plus infinite, is concave up. So all the things that from here that we found, they are all correct. Let's check this one. When x goes to plus infinite, results are also going up to plus infinite. When x goes to minus infinite, the results are also going down to minus infinite. Thanks for listening. I hope that this video will be helpful for you.